Hopefully what we'll finish today is all of our chemical reactions so we can spend the rest of the time talking about conversions. What we're looking at is classifying chemical reactions. Right? Some of these you're responsible for more information than others. Okay? Ultimately what you need to be able to do is look at a chemical reaction and say that is a combination, that is a decomposition, that is a single replacement, that is a double replacement, that is a neutralization, and the last one, which isn't unfortunately on the slides but does show up later on, combustion. So you have to be able to look at a given chemical reaction and make that classification. Right? Some of these are just shown in black up above. Notice they're generic. AB, AB goes to A plus B. What element is AB? Or what element is A? Sodium. What element is A? It's not an element. It's just an arbitrary symbol. All we look at the periodic table, there's no element that's just A. Okay, it's an arbitrary symbol. Okay? So all we're trying to do is show that this thing can break apart into pieces. When it breaks apart into pieces, we have a decomposition. So in a decomposition, we start with how many things? One. When we end, we have more than one. Okay? In this specific example, we're showing 2, but that could be 3, 4, it could be infinite. Okay? Combination reactions, what do we start with? More than one thing, what do we end with? One thing, because we've combined them into one thing. When we look at the single replacements, didn't we talk about these? Did I not use my horrible analogies yet? No? Okay, we'll use the horrible analogies. Single replacement reactions. We're taking the most similar species and we're exchanging them. Okay, so we'll use my horrible analogies. Okay, B and C. I get to be C because I'm just average. Okay, B was my first girlfriend. Okay, that was a pretty horrible relationship. Thankfully, my wife came along and said, "Get out." And now I'm with my wife. And my ex-girlfriend now is by herself. So it's a single swap. We're exchanging the similar thing. Okay. Because it could have been the other way, right? Like my wife could have exchanged with me, and then I would have been the one on the left out, and that wouldn't be fun. Okay? So we're exchanging the girlfriends in this case. Okay? Typically, it is the positively charged species. That's why it's color-coded to show blue cation. What species are typically cations? The metals. So typically, when we're looking at a single replacement reaction, we're exchanging metals. It does not have to be metals. It's typically something that's positively charged. Okay? What is something that is positively charged that is not a metal? Boron's a nonmetal. And, well, true, and it's positively charged, so that does kind of work. Give me another one, because you won't see boron all that commonly. Ends in gin. Hydrogen. Hydrogen on the left side of that staircase is classified with our metals. Why? What is the charge on hydrogen typically? Positive. There's the cation. Okay? Because we started with this horrible analogy, we could continue with it. Oh, actually, we could make it a little bit better. Okay? My first girlfriend and myself, my wife and her first boyfriend. We decided those were awful pairings. So my wife traded to now pair up with me. Okay? So we're seeing a double replacement. Okay? For lack of a better description, a full wife swap. Okay? Or a full husband swap, if you will.
There are TV shows about this.
Okay? Yeah, there are all sorts of fun TV shows on that. Okay? We're doing a complete exchange. Again, what are we exchanging? The similar things in each species. Okay? I can choose to exchange the blue things, or I could choose to exchange the red things. Either way, I end up with the same result. Kind of make sense? Okay. Neutralizations. When we go through and look at the neutralization, that should look kind of familiar, because what is the neutralization?
Single replacement.
Single replacement?
Double replacement.
A neutralization is a double replacement. There are two pieces. We're doing the full swap.
Isn't neutralization
Okay.
even like not necessary though?
Why do we call or have neutralizations? Why are these called out extra if all they are is double replacements? Before this class, how many of you have heard of double replacement reactions? Before a chemistry class, how many of you have heard of double replacement reactions? Before chemistry class, how many of you have heard of acids? Ooh, that's kind of interesting. You didn't have to have chemistry knowledge to have heard of an acid. So why do we call out neutralization reactions? They involve acids. Okay? We have a hydrogen in front. What should we see as a subscript right after? AQ, because that means acid. Hydrogen in front and AQ is your definition for acid in this class. Okay? Why do we call attention to it? Because acid-base chemistry or neutralization reactions are so overwhelmingly common that we see them in lots of different places. That's why we call them out as a separate reaction category. Okay? The combustion reaction is just a reaction of carbon or a carbon-containing substance with oxygen. Interesting feature with our combustion reactions is that they will always produce carbon dioxide and water. Okay? Again, for the sake of this class, that's what they do. Okay? None of these are balanced at this point. This is just saying how do we classify them. Okay? Kind of makes sense? Okay, so let's look at an example. Combination reactions. Your textbook goes through and lists out a whole bunch of different pieces within this. Each time we look at a different reaction, there's new things that we have to think about. And which reminds me I should go back, actually. Of course, the internet's having problems. There we go. When we look at our reactions, each thing has layers of information. Notice for the single replacement, double replacement, and neutralization, we started color coding stuff. Why did we color code stuff for those, but we didn't for the other ones?
Because the charge is important.
The charges aren't important for the combination and the decomposition. Are they important for the others? Yes. Okay, so it helps us to process that information. Okay, which gets us to kind of the next fun feature. Because more information is specified for the single replacement, double replacement, and neutralizations, what do you think we expect from those types of reactions? More or less? More. You're given more information, okay, within our blank formats, which means we expect more information from you. Turns out, for the first two reactions, what are you expected to be able to do? Recognize, and recognize alone. Okay? I just want you to be able to look at a reaction and be like, that's a decomposition, that's a combination. Okay? You're not expected to predict products, reactants, any of the above. You just need to be able to recognize it. How about for single replacements, double replacements, and neutralizations? Not only do you have to recognize, but you now also have to be able to predict. Okay, you have to predict the products. Okay? In some cases, you have to predict what the products are of that reaction. You also then have to predict, did the reaction occur? Well, how do we know what chemical reactions happened? Did we have a slide where we had 4 things that said,
A solid is formed.
if we form a solid, we know a chemical reaction has occurred.
Energy is released or absorbed.
Energy is released or absorbed. A change? Color change. A permanent color change, yes.
And also phase change.
Phase change, you already kind of said that with solid. Ultimately, what we're saying is the formation of a gas. Really, a phase change is a much broader term that makes more sense to apply. It's saying, did you change phases at all? Typically, it's solids and gases. Why? What do we mix?
Two.
Two liquids. Usually those liquids are dissolved in water, so we end up with aqueous solutions. How would we know we have a new phase if I start with two liquids? Solid and gas. Those are very clearly different things. What if my two liquids produce another liquid? Would I be able to tell that a liquid had formed? No, unless something else happened. Okay? So a change in phase to a liquid, while it is a chemical reaction, not very obvious to determine. Okay? So we really have to look for those solids and gases, which means when we get into our single replacement, double replacement, and neutralizations, not only are you expected to be able to predict what the actual products are, you also have to predict the phases. Once you have the phases, you can then establish, did a chemical reaction happen or not? Okay, so a lot more information goes into those reactions. So when we look at the textbook for a combination lists 3 different types of combination reactions. Okay? And they go through and say, well, with this information, you should now be able to predict what happens. So if I look at the reaction of a metal with oxygen, let's say lithium plus oxygen. Okay? If I'm looking at oxygen, what's my symbol? Why is it O2? It's a diatomic element. And if I looked at the product, what would my product be? LiO2 was a suggestion. We have a red 2 and a purple 2. Everybody see the red 2? That's a yes. Everybody see the purple 2? It's also a yes. Are those 2's the same thing? No, they have entirely different meanings. They're both subscripts. They're both right after the oxygen, but they mean very different things. Why is there a red 2? Because why? Nope. You guys actually said earlier why it's a red 2. It's diatomic. Why should there be a purple 2? I need to balance the charge of my elements in that compound. And when I balance that charge, what should the overall charge be? Why do I know it needs to equal 0? That's our rule. Whenever we're doing chemical reactions, we are making neutral compounds. So, is that purple 2 correct? What is the charge on lithium? What is the charge on oxygen? -2. Is that purple 2 correct? No. Why was that purple 2 brought over? Since you were the one that said it, well, why did you think to put the purple 2 there?
I was predicting.
Why were you predicting it, though? What about this made you say, I want to put a 2 there?
It's just something plus something equals something.
Well, there's a 2 on this side, right?
Yeah.
If I'm just going to combine these, what's going to happen? Well, I should just combine them and get the 2 there. The combination does not say how much of those pieces necessarily come together, just that they come together. Which means this formula is incorrect, and it must become Li2O. Does this still match the pattern of a combination? I'm taking a substance with another substance to make one substance. That's a combination. Okay? The next question that may come out of it, you might say, well, but that's not balanced. That's also irrelevant. Okay? As a combination reaction, this is the basics of it. Is it a balanced combination reaction? No. How do you balance it? Okay, so our balancing process, where do we start? Lithium in the middle. How many lithiums on the left? 1 and
2.
Is that balanced? What do you need?
2.
Now we do oxygen. How many oxygens on the left?
1.
On the left. 2, because of the 2 there. On the right? 1. Is that balanced? No. So what do you do? You need a 2 there. So the oxygen's balanced. Now what do we do?
Go back and start over.
We've changed numbers. The instant you've changed numbers, you must go back and check again. Lithium. How many lithiums on the left? Sorry. Yeah, on the right?
4.
4. It's not balanced. What do you need to do? Okay. The number on the left needs to become a 4. Oxygen's on the right.
2.
Oxygen's on the left. 2. Is the oxygen balanced?
Yes.
We change the number. What do? You go back and you balance it. Or you check again. What are you going to find? Now it's balanced. Is this still a combination reaction? Yeah. I don't care how many of each of those species gets involved in the reaction. All I care about is that I start with 2 different types, at least 2 different types, and I end with 1 type. That's now a combination. Okay? The reason the textbook calls attention to this is they're saying you should be able to predict this reaction. Okay? Were we able to predict it? Okay? So let's try another one. Let's take iron now with oxygen. What do we make?
Iron oxide.
We make iron oxide. Okay? Iron oxide is a name. Is that a good name?
No.
No, it's actually a bad name. It's an invalid name. Why is it invalid?
Because iron has the charge difference thing.
Iron, you are not required to memorize the charge on, which means that could be iron 2 oxide. That could be iron 3 oxide. That could be iron 4 oxide. We don't know the charge. How would we determine the charge?
The oxygen.
From the correct chemical formula. Were we given the product? No. Can we predict this combination reaction? No. This is why, as a blanket statement, you are not responsible for predicting combination reactions. There's too many different possible outcomes that could come out that makes it difficult to go through and predict. The examples the textbook provides are nice. They're extra information that would allow you to potentially come up with the starting points for a product, but depending on the question asked, you may not be able to finally predict them. So in this case, we actually can't predict which iron oxide we formed. We don't know how much iron is there. We don't know how much oxygen is there. Those are unknown variables. The only way we would find that out is if we were given more information. Okay? So for our combinations, you are not expected to predict. Okay? For the sake of homework, should you be able to predict? Yes. Why in the homework are you allowed to now predict things when I just told you you don't have to?
Practice.
What do you have with the homework that you don't have with an exam?
Ability to check if they're wrong.
Not quite.
So, what, self-owned?
A textbook. A textbook that goes through and says what those extra rules are for how you run that reaction. That's how you figure out the homework. Okay? The homework is there to help guide you and give you that practice. That doesn't mean you're necessarily getting tested at that level. Okay? So let's take a look at some reactions here, because you have some basic experience with those 4 or 5 different types. I want you to go through, for each of these, determine the reaction type, predict the product, and balance the reaction. Okay? And 1, 2, 3, 4, 5, 6, 7 questions, 10 minutes. You have to have a hydrogen. Well, doesn't this have hydrogen?
Has that hydrogen up front?
It has to have the hydrogen in front. That hydrogen's not in front, so we don't have an acid. That's our basics behind that. Okay? You mean we have to use all of those nomenclature rules to help us? Yes. If at any point you have a weakness from pretty much the beginning of the semester all the way through now, you're going to have a really rough time. You have to be constantly manipulating these things. Okay? So let's clean up some space here, because this is one that we could potentially balance. So it's not neutralization. So what's another option?
Double replacement.
Double replacement. In the double replacement, okay, we have AB plus CD, and we do the exchange. I'd end up with AD plus CB. Okay, so 2 things to 2 things. Does that look right? Do I have 2 things to 2 things?
Yes.
Yes, so it fits the basic pattern there. Molly, you're shaking your head no. Why not?
Because I think, I could be wrong, and I'm not saying I'm right, but like, I feel like because that's a single thing, wouldn't you have to have two things there? in order
C,
to-
D, are those things different?
Yeah. So we
How do we know they're different?
It's representing another element, but there's not another element there. So-
Writing systems? How do I know C is different from D?
So it's a single replacement.
How do I know C is different than D?
They're not the same.
Two different letters. Okay? The format gives me that. If I overlay that on top of the reaction above, is O a different letter than O? No, this doesn't fit the double replacement. Okay? There was an option for potentially running the single replacement. Okay? Again, two different things. And actually, if we erase this more appropriately, it's probably more like this. Okay, switching up the order. AD and then B by itself. And that exchange for the single replacement, we're exchanging the most similar things. Remember, the color coding had A and D as blue. And in particular, those two elements were labeled blue because they were cations. And we said most commonly, those cationic species need to be metals. Is carbon a metal?
No.
No, carbon is not a metal. Is hydrogen a metal?
No.
No, it could act like one, so maybe we've got an option there. Oxygen a metal? No. Does that fit our pattern? No. So not double replacement, not neutralization, not single replacement. Right? Combination. What is combination? Smash two things together. Do I have two things? Yeah, so it's a combination. But I smashed two things to make one thing. Did I make one thing? No, so it's not a combination. Maybe it was a decomposition. Decomposition, I end with multiple things. Do I end with multiple things? Yeah, so it must be a decomposition. Except in a decomposition, what do I start with? One thing. Do I start with one thing? No, what do I start with? Two things. That doesn't match any of those 5 things that were listed. Except, remember I said there was a reaction that was left off of this, and I hand wrote it in at the bottom. And I said a combustion reaction, which was carbon reacting with oxygen. C means carbon. Let's do some decoding here. O2 is oxygen to produce CO2, carbon dioxide, and H2O, water. Oh, you mean that fits exactly a combustion reaction? Yeah, it does. Yeah, that would be a combustion reaction. That would be the reaction type. Do you need to predict the products? Are you responsible to predict products for a combustion? Yes, because what are the products for every combustion reaction? CO2 and water. Okay, do I need to predict the products for this reaction? Okay, the answer to this next question is 2. Do you really need to answer that question?
2. Yes.
I gave you the answer. The answer is there. Do you have to write the answer? You don't have to balance it. What was the question? Do you have to predict the product? Do you have to predict anything? No, why not? It's already there. Okay? Use the information directly in front of you. This is not one that we have to stress about predicting product on because it's given to you. Okay? It's processing small bits of information. If you choose to not process the information that's there, then you can get to the wrong answer very quickly because you aren't using the information that's given to you. You have to use the information that's given to you. Okay? Which sets us up to actually the hardest part of this one, which is balancing the reaction. When we go through, When we go through to balance the reaction on this one, why does this one become so much more difficult?
Because of 2.
We start with carbon 4 and 1, not balanced, so I make a 4. Move to hydrogen. How many hydrogens on the left? 10. Hydrogens on the right?
2.
2, because of the subscript. Okay? That's not balanced. What do I need? I need a 5 in front. That now gets me 10 hydrogens, because I have 5 H2Os. Okay? H2O, H2O, H2O. What do I got? 4? H2O. How many times do we have hydrogen written in that? 5. Fair enough. H2O is HOH, 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 HOH. How many times do you have hydrogen written? 10. You are responsible for knowing what that formula means. There it is, HOH. You are responsible for knowing that 5 means this multiplies through for all of them. Okay? If you are weak in any of that, that makes the rest of this miserable hell. Okay? So you have to recognize those patterns. That's why we talked about those patterns. Okay? That's why we addressed them, and you said, okay, we get it. And we moved on. Yes?
So why did you do the hydrogen first?
Okay? We'll get to that one in just a second. So this is now 10. We could move to the oxygen. Why would I do hydrogen before oxygen? This comes from experience and how we balance. Turns out that hydrogen and oxygen can be tricky to go through and balance. We typically stick with the non-hydrogen and oxygens. Why would I pick hydrogen before oxygen to balance? When I take a look at hydrogen on the reactant side, how many different places does it show up? 1. How many different places does it show up as a product? Hydrogen, 1 place. How many different places does oxygen show up as a reactant? How many different places does it show up as a product? 2. Because it shows up in multiple different locations, I'd have to be changing numbers in 2 different spots. That can make it difficult to balance. So I don't want to balance oxygen, because ideally, I can do everything else, and then I get to oxygen, and what happens? Everything would be balanced, and I don't have to worry about it. I don't have to deal with that issue. Unfortunately, what happens in this case? How many oxygens on the left?
1.
Oxygens on the left?
2.
2. Why is it not 1? You have to watch out for the subscript. The meaning of those numbers is important. Okay? How many oxygens on the right?
18.
Okay. We have 5 coming from water. And we have 2 in CO2, but I have 4 CO2s, meaning 8. 8 plus 5 is 13. Can 13 and 2 ever equal each other? No. One's odd and one's even. How do we fix that? Well, just like with balancing charges, what we need to do is find the lowest common multiple that allows them to equal out. What is the lowest common multiple between 2 and 13? 26. Right? How can I make that 2 26? How do I make 2 a 26? Multiply by 13. Okay? That becomes really challenging on the other side. How do I make the 13 2? Sorry, 26. I'd have to multiply by 2, but because my oxygen is in 2 different locations, that's really challenging to deal with. So what am I going to do?
Start over.
I'm going to start over. Whoa, wrong eraser. Okay. In this starting over, what I need to do is come up with a reason for why we're resetting. Okay. I somehow multiplied the oxygens by 2, right? In 2 different locations. What's the easiest way to make sure I'm consistently multiplying the oxygens by 2? If I just multiplied this number by 2, did I get 26?
I don't know.
Why not?
26.
Why do I want 26? What was the lowest common multiple between 13 and 2? 26. What do I want to get? 26. It's the lowest common multiple because that is the only place that I can make the oxygens equal each other. Okay? I can't multiply by fractional values to get this out because that means fractional molecules. Okay? So if I multiply this one by 13, great. If I can multiply this 13 by 2, I'd get 10. Or 13 times 2 is 26. Okay? What could I do to these numbers? If this gets multiplied by 2, what would I theoretically have to do to these? Multiply those each by 2. How did I get the 8? 4 times 2. What am I multiplying by 2? The 4. Which means the 4 becomes 8. Okay. What happens to the 5? Becomes 10. Okay. And as someone astutely just pointed out, that changes all the numbers. Literally with every other balancing, the lithium to oxygen one that we just did, we changed the numbers and had to cycle through that 3 times before it balanced. When you go through to balance an equation, you have to cycle through multiple times. If you go through once, you probably screwed up the balancing and it's not correct. Okay? Yes, that changes all of the numbers, so now what do? We restart the entire process. How many carbons on the left? 4. How many carbons on the right? 8. Because there's an 8 in front now. How many hydrogens on the left? Whoops, sorry. Carbon's not balanced, right? How do we fix it? We need to put a 2 in front. Now we have 8 carbons. How many hydrogens on the left? I would now have 20. How did I get 20? There's 10 in the compound with 2 of those compounds. How many hydrogens on the right? There's 2, but 10 of that compound, which means 20. What should I move to now? Oxygen. How many oxygens on the left?
26.
26. There's 2, but I have 13 of those sets. Oxygens on the right. 8 times 2 is 16. 10 times 1 is 10 equals 26. Did it balance? Yeah. Is there a lower number I could choose? There's a lower number. That means I could divide everything through by a whole number to get a lower whole number. What could I divide 2 by to get a lower number than 2? 2. Okay, fair enough. That's absolutely valid. You could do that. But if you divide that first one by 2, what do you have to do the next one? You have to divide everything by 2. Is 13 divided by 2 a whole number? No. Can we have a fractional molecule? No. That is your correct equation. Okay? Your combustion reactions have the potential for this sideways thing coming at you. Okay? It is hard to deal with because you're dealing with these odd values in it. Okay? There are other methods to go through and do it. Ultimately, they're all doing the same thing. You could go through and say, well, it didn't balance. Okay? Multiply everything by 2. Try and balance it again. Okay? It also works. You could multiply or balance it at 13 halves. 13 halves isn't a whole number. How would you make 13 halves a whole number? 13 halves would be 13 divided by 2. Multiply everything through by 2 and you would get those same numbers. Okay, so the combustion reactions have the potential to be a tricky balancing. If you aren't comfortable with balancing, don't attempt them. Because what's going to happen? You're going to get it wrong. And you will have spent tons of time balancing a question that you were going to get wrong anyway. How many people got beyond question 1? How many people got question 1 right? Okay. Very few people got beyond question 1. Hardest question on the whole freaking slide. Okay. This is where having an idea about some of that content can help you skip through. If you don't have any idea, you have no idea where to start. You start with potentially the hardest question. Okay? All that ends up happening, you end up suffering as far as a grade. You have to know some content. This content has been given to you time and time again. Okay? Next one. Lithium metal reacts with bromine gas to produce. So if we started this reaction out, what would we convert this to? Li, good first step. I like it. Plus
BR2.
Br2. How did you know it was Br2?
It's part of the hockey stick.
It's part of the hockey stick. Acceptable. To produce. What type of reaction is this? Combination. Are you expected to predict combination reactions? No. Next question. Okay. If you aren't expected to do it, don't do it. Could you predict the product for this one?
Yes.
Yes. Okay? And that's fine. You could go through and do it, but again, you're not responsible for it. The next one. Sodium hydrogen carbonate decompose into. Can you tell me what sodium hydrogen carbonate is? NaHCO3. Okay? To produce. What kind of reaction is this? How do you know it's a decomposition? Because it says decompose. Okay? So now that you know it's a decomposition, should you predict the product? No. Why not? You are not responsible for predicting products in a decomposition reaction. What we literally just said is that you just need to recognize it. Given more information, could you predict it?
Yes.
Yes. We aren't there yet. Next one. Aqueous sodium chloride reacts with aqueous lithium nitrate. Sodium chloride.
NaCl, AQ.
NaCl, AQ plus LiNO3. Also AQ. Okay, reacts with. What kind of reaction does this fit? Double replacement. Are you expected to predict double replacement reactions? Yes, which means? Okay. One way to do it is just start shouting out the answer. It's LiCl and NaNO3. As part of our double replacements, not only are you expected to predict the product, you're also expected to predict the states, the phases. Okay? To determine the phases for double replacements, what information do you need to know? Also in the play posit video, you would need to know solubility rules. Anybody see the solubility rules listed up there? No. If they aren't listed up there, do I expect you to memorize them?
Yes.
I give them to you. Also in the play posit video, it says, I give you this. Take a look at exam 1, front of the exam. You'll see a little corner, a little box, and in that box it says, solubility rules. Because I give them to you, I don't expect you to memorize them. Would you be able to predict the phases given the information in front of you? No. Because you don't have the solubility rules directly in front of you. So you don't have to stress about that information. Okay? Should you be able to verify that these structures are all indeed correct? Yes. How do we determine that? I heard someone mumble it. Balancing the charges. What is the charge on lithium? +1. Charge on chloride? -1. Is that the correct formula for lithium chloride?
Yes.
Yes. What is the charge for sodium? +1. Charge for nitrate? -1. Is that the correct formula?
Yes.
Yes. Okay. Could we balance the reaction? Now that we have products, should we be able to balance the reaction? Yep. So we could go through and balance it. Why is this reaction nice? It's already balanced. Okay. Next one. Zinc plus lead sulfate. Heard someone shout it out? Yeah? Zinc is a metal. Pb is lead, which is also a metal. Sulfate is non-metal. Do we have two similar things? Yep. What does this look kind of like? Single replacement. Are you expected to predict single replacement reactions? Yes. You are absolutely expected to be able to predict the products of the single replacement because it's the girlfriend for wife swap. I get Pb by itself and I get zinc sulfate. Okay. You are expected to get there. Is zinc sulfate the correct formula? Did I draw that correctly? How do I know? I have to balance the charge. Where did we get lots of practice with balancing charge? Begins with an N. Nomenclature. I don't care that you get the name. I do care that you recognize how to balance charges. That's the important part in nomenclature. If you run crossover method like the textbook suggests, you've lost the ability. Okay? Zinc is what charge? A +2. How do you know it's supposed to be a +2? You are told to memorize that. Sulfate is a -2. How do you know that? You were told to memorize that. If you haven't been memorizing, you're going to have a really rough time next week. Next week is the exam. Okay? So if we go through and look at that, is that formula correct? Yes, the charges balance out. Question? The exam is Thursday, I think, next week. I have to check, but I think it's Thursday. Okay. The next part with our single replacements, we are officially responsible for phases-ish. Okay. The single replacements get a little bit easier. Okay. The species that is by itself is what phase?
Solid.
Solid. How do you know that?
Says it.
Yeah, because you look at the reactant and the species that's by itself is what phase? A solid, which means when we move over to the product, the species that is by itself is solid. Match the pattern. As far as the zinc sulfate, it's a bit iffy to go through and call it aqueous, but we could go through and call that aqueous as kind of an outright jump in our single replacements. Why would we do that? We're trying to not complicate things by bringing in solubility rules from the double replacement. Sulfur solid reacts with oxygen gas to produce sulfur dioxide. Symbol, sulfur solid. S. Plus
OXO2.
oxygen gas. What kind of reaction does this look like? Looks like it fits a combination. But I don't have to predict products on a combination, so I'm done. Why do I have to predict that this is now SO2? Because it tells you that it produces it. You have to do that translation. Right? Fits the combination reaction. Now that it's combined, we could theoretically go to balance it. What's nice about this one? It's also already balanced. Last one is another single replacement, because we're going to look at that in a second. We're going to skip over that last one. Yeah?
So on this, so in this case, the sulfur solid reacts with oxygen gas to produce sulfur dioxide. The reason that you had to write SO2 is because you're not doing analysis in that case. You're doing translation or reporting into the numerator system.
So
I've already given you the information. It's your job to show that you know how to translate.
So if you go through and look at each of these, your combinations and decompositions are just a reporting. Okay? Report the information that is given to you. Okay? To a certain extent, you do have to do an analysis because you have to decide that this is a combination reaction. Okay? But it's relatively superficial. Okay? The single replacements, double replacements, and neutralizations all become significantly more difficult because you have to do an analysis of what's happening on the reactants to predict the products. Okay? You have to analyze those products further to specify phases. In the single replacements, and for that matter, the double replacements, you will also now have to analyze the analysis to decide, did that chemical reaction actually happen? Okay? So for your single replacements and double replacements, there's layers upon layers, okay? Like an ogre. I heard a boo and a laughter. That worked out well.
Ogre in onion.
Okay. Decomposition reactions. The one off the previous slide was, what does sodium hydrogen carbonate decompose into? We wrote it out and said, well, that was a decomposition. I'm not responsible to predict the product. You're not. Are you now? Yes. Why now? Because there is given information directly above. You need to use that given information to help you predict your product. Okay, so what did we start with? Sodium, Na, H, hydrogen, carbonate, CO3. What does it decompose into? Well, given information, a metal hydrogen carbonate. Metal. Which of my species is a metal? Sodium. A metal hydrogen carbonate decomposes into, and this is an unfortunate aesthetic aspect of writing because the metal and the carbonate are on separate lines and really those should be combined. Okay, almost technological too, right? Metal carbonate. Okay, what is the metal carbonate? What is the metal?
Sodium carbonate.
Sodium. What is the carbonate? CO3. Okay. And what? Water. And? Okay. Because you have that generic information above, you can come to that conclusion. Without that generic information, you can't come to that conclusion. I do not expect you to memorize that. Okay. Is this the correct answer? No. Why not? What's not balanced? Okay, the number of elements, that's a good place to start. Unfortunately, we shouldn't even be balancing the equation. A compound. Sodium has what charge? A +1. Carbonate has what charge? -2. How do we know -2? You were told to memorize it. If you have not memorized it, you can't answer the question. Is that formula correctly balanced? How do we correctly balance it? We need 2 sodiums. I'm not putting a 2 out front, because if I put a 2 out front, what does that 2 apply to? That also applies to the carbonate. That messes with the whole balancing aspect. Now that I have a proper product, now I could balance the equation. Is the equation balanced? No. When we see that right away with sodium, there's 1 versus 2. How do we fix it? Put a 2 in front. How many hydrogens? 2 and 2. Where's my pen? There's my pen. Oxygen or carbon. There would be 2. On the right, how many carbons are there? 2. Is the carbon balanced? Oxygen. Sorry, it's kind of crowded. There's 3, but 2 of those, I get 6 oxygens. Oxygens on the right. 3 plus 1 plus 2 gets me 6. Is it balanced now? Yes.
When you guys were solving some of that, you initially had to jump back and go, oh, whoops, all the way back to the beginning of that complex compound, right? And look for the coefficient.
Coefficient, yep.
Right? So that's the sentence. So you're really trying to read that whole compound. And that people do that with writing sentences too, so make sure that you just did that here. It's also something you might do in an alphabetic sentence as well. So always go back to the beginning of the sentence and make sure you're reading it in context. In the same way, you have to read, the more complex these compounds are, the more you're going to have to draw yourself back to the beginning to make sure you're processing all the information, not just part of it.
So your more complex sentences have different parts. Those different parts can operate on different parts of the sentence, which can change a lot of the meaning. So depending on your cognitive uptake of the sentence, you may actually have to remind yourself of what you already read to get to the meaning of what the sentence was. I would argue that's a bad sentence, but
Or complex, this is a
Yeah.
chemistry sentence, it's a complex.
but yeah.
Yeah.
So single replacements are a fun one. Okay, let's take a look at two examples. We saw the zinc plus lead to sulfate. Okay, so if we predicted that out, we get zinc sulfate plus lead by itself. Let's take a look at the one written in text right above it. I take iron plus copper sulfate. How do I know there's only one copper in there? It says copper 2.
Oh, yeah, there's 2. Plus 2 and negative 2.
The 2 is the charge on the copper. What's the charge on sulfate? Negative 2. I only need one copper to balance the sulfate. Okay, to produce then what? It's a single replacement. Iron sulfate plus copper. That's awesome. Is iron sulfate a proper name? No, I'd have to be more specific to it. It could be iron 2. Couldn't this also be iron 3? I predicted the product here. So could that be iron 2 or iron 3? Could be either one. How do I know which one it is? You're assuming that sulfate forces that chemistry. Sulfate has nothing to do with that chemistry, unfortunately. How would we know that that was the proper formula? You don't. That is a horrible sentence to have you predict products on because you don't know the charge for iron. If you don't know the charge for iron, you can't properly predict this. You see questions like this pop up in the textbook all the time. You won't see questions like that on the exam because on the exam, I ask what's written right above the zinc and lead, where you are now required to be able to predict because what is special about zinc? You have to know the charge on zinc. That's why you can predict that properly. For the bottom one, you don't know the charge on iron. You can't predict that equation properly. Okay? If it shows up in your homework, what can you do to get an answer down to work with? Assume it's a +2. It is a horrible thing to do, but that's what the textbook's expecting you to do. Okay? So, let's erase that bottom one because that's ugly and it just bothers me that it's there. And we'll erase that sentence. What is a chemical reaction? Or sorry, a chemical equation. It's that. A chemical equation is a plan. Okay? If you all won $1 million right now, what would you do?
Make a plan.
Okay? Buy your own house. Invest it. Okay? What have you come up with? We even had one that was very blatantly honest. I would make a plan. Okay? Some of us have plans for if we win $1 million. Okay? That's a chemical equation. It's a plan. It does not mean it occurred. How do I know a plan has actually happened? Well, if it was $1 million, someone would have to come up and be like, here's a bag of $1 million. I'd have to see that to believe it. How do we know that happened here? If we saw a chemical change. How many of you can see a chemical change for a reaction in the lecture? You can't. Why not? What are chemicals? Physical objects, liquids. They're kind of dangerous, right? Okay, so they're so dangerous that what do we make you do? Wear protective equipment. Okay? Work with them in a specific place where we don't contaminate the rest of the world, okay, or the rest of our classrooms. Okay? Why can't you do that in the lecture? It's not the lab. It's dangerous. Okay? So we change the expectations. We shift all that danger to a special location. We have our own little danger zone. Okay? In the lecture, how are you supposed to predict that that happened then? We can't do a chemical reaction to prove it. What we will do instead is rely on somebody else to have done that work for us. We just have to interpret their results. What is their results for a single replacement reaction? An activity series. So when we look at this activity series, let's get our plan back up here. What are we going to be looking for in that activity series? Okay, lead was a good first guess. And zinc. Why would we pick those two things? So is gold.
Because they're in the formula.
They're in the chemical equation that we're being asked to predict something about. Okay? Never assume. I don't like being yeah. Okay. Ranking activity. The higher up on this, the more active you are. Well, what does activity mean? You have lots of probiotics. Yeah, never mind. Don't worry about it. Okay. If it's more active, it's more likely to react. So the higher up on this, the more likely it reacts. If it reacts, what is it with? Is it by itself if it reacts?
No.
No. So the more active it is, the more likely it's in a compound. What if it's less active? So we could do less likely, but that's negative. We want to be positive. More likely not a compound, or more likely alone, okay, or solo. Okay, so let's go through and use this information. Zinc, higher up in activity, so that means it is more likely in a compound. In my equation, in my plan, where is zinc in a compound? Okay, so let's try it this way. The symbol for zinc is Zn. Where does the symbol Zn show up? Both sides of the equation. Okay, there are those two sides. Okay, where is zinc with something? On the right side of the equation. How do I know it's with something? There's something written next to it. Okay? Next part. Lead. Lead is less active, which means it is more likely to be alone. Where's lead in my chemical equation? It's on both sides. Where is it by itself? On the right-hand side. Where did I star? On the right-hand side of the equation. When I run this reaction, what am I mixing? Anytime you run a reaction, what do you mix? Two things. What are those things? The reactants. Where are the reactants in this chemical equation? On the left-hand side of the equation. I mix these two things, what happens? What does zinc decide to do? It wants to be in a compound, so what does it do? It kicks lead out and becomes a compound. Does this chemical reaction occur? Yep, that's where it's favored to be. This is a favored chemical reaction. We've now used the activity series to predict that this reaction does occur. Well, would this work to prove that a reaction did not occur? Let's look at the very bottom one. Gold and copper, right? So if we did our prediction, we'd have gold with sulfate, and then we'd have copper all by itself, yeah? Yes. Where is gold? Where is copper? Gold's at the bottom, copper's up here. Copper is higher in the activity series, which means what does copper want to be? With something. So we go and look at our equation. Where is copper with something? On the left-hand side as a reactant. Gold is lower in the activity series, which means it wants to be alone. Where's gold by itself? On the left-hand side. I now mix the reactants, which would be gold and copper. Okay? The plan is that gold would go to become sulfate. Does gold want to be in a compound? No, because I started on the left. So what do I get with at the end of this chemical reaction? I get the exact same thing I started with. No chemical change occurs. There's no reason for a chemical reaction to occur because those species start happy. We're using the activity series to predict whether things shift back and forth. Kind of makes sense? Get you a fun little idea to end on. Gold versus lithium. Which one's our currency based off of? Gold. Why is it not lithium? So one option was you can purify gold. You can purify lithium. You can get lithium very, very pure. Doesn't oxidize. What does it mean when you oxidize? Not necessarily decompose. You react with oxygen. Okay? Gold doesn't react with things. Okay? If gold reacted, what phase would it become here? Aqueous. Okay? If lithium was our currency, what happens? Okay? All we got to go in and do is attack Fort Knox with water balloons. Lithium will react with water to turn into lithium ion. Where does that lithium ion then do or go? Down the drains in Fort Knox. What happens when I shoot water at gold? Nothing. It's chemically inert. It doesn't react. The only reason gold is valuable is because it does nothing. That's why it's valuable. If it did something, we would lose the presence of it over time. That diminishes its value. Okay? Like your money in your wallet. Okay? If you had 40 bucks in there, eventually what happens over time to that $40? It spends and you no longer have that. Okay? So if someone comes up to rob you after you get your paycheck, you're kind of upset. If someone robs you 2 days before you get your paycheck, probably like, have fun with the wallet. You can put some money in it if you like. Right? Same thing is happening with our elements. It has something to do with their reactivity.